So, dear students, welcome to the another lecture of digital control system. In this lecture, we will understand about the zero order hold. Now, what is zero order hold? Zero order hold is nothing but it is again a hold circuit, and the order of this hold circuit is zero, right? Now, how do we come to know that what is the order of this circuit? So that we can make out from the transfer function of the given circuit, right? So if the order of the circuit is 1, so that becomes first order hold. If it is second, then it becomes second order hold, and so on, right? So to understand the zero order hold, uh, let us consider that there is a sequence. So given a sequence, right? And this sequence is, for example, y0, y1, and there is some kth sample, output sample, and so on, right? Now, because we have to construct this YAT from these samples, right? So how will we construct? Okay, so now we have to construct YAT. YAT is basically the analog signal. So for t greater than equal to 0, right? Now, how will we find out this YAT from the given sequence? So YAT can be obtained by using the YAT can be obtained by using the Taylor series expansion. Sorry. So if we use Taylor series expansion, so we will get, so for t is equal to kt, we can express YAT, right? So YAT is YAKT. So this is, we are expanding this about t is equal to kt plus YA dot kt and t minus kt plus y double dot a kt and t minus kt square divided by factorial 2 and so on, right? So here this t lies between kt and k plus 1 t, right? So now this YAT, sorry, KT, this is actually the first derivative of Y, right, with respect to time for t is equal to KT. Okay, so this can be taken because this is a sampled value, means this is the analog value which is obtained from the given samples about t is equal to kt, right? That means the whole time period t has been divided into k samples, each of which is of time period t. What does it mean? It means that you have like so many samples, k samples, right? K samples, and every sample, successive sample, has the same time period t. So if you multiply all these k sample with the, because this time period is constant, so k into t will give you the whole time period for which the signal exists, right? So this is equal to one, you can find out this from the difference equation. So the difference equation of this particular form is y a kt minus y a k minus 1 t, right? So uh, this is, right, so this is the difference equation form of the given dy by dt, means this particular term, this one, right? So uh, this represents the change in the value of the signal, right? Similarly, this particular term, this one, okay, so this particular term is given as y dot dot a kt is equal to d square y a t by dt square at t is equal to kt, right? So uh, we can write this as, because this is the second derivative, because we have two dots here, so two dots means second derivative of the signal. Okay, so it would be written as 1 by t, and this is expressed as the difference equation of the first derivative. So first derivative is y dot a kt and minus y a dot k minus 1 t, right? So, and this is bracket close. Now we can replace this y, we can replace this equation, we can put this equation here, right? And by replacing k with k minus 1, we can have the replacement of this particular term. So let us say this is equation number 1 and this is equation number 2, for example. So you can write y dot a k minus 1 t is equal to 1 by t. So y a, we are replacing k with k minus 1 here. So it is k minus 1 t minus y a k minus 2 t. So this is, let us say, equation number 3. Now what we will do is we will substitute equation 1 and 3 in equation 2. So substitute equation 1 and 3 in equation 2. So this will be, so we have y dot dot a k t as 1 by t square. So we can simplify this equation. So it is 1 by t square y a k t minus 2 y a k minus 1 t and my plus y a k minus 2 t, right? So this is, let us say, equation number 4, right? So in the given equation, equation number, if we go back the previous slide, so if we see this particular Taylor series expansion, right, this one, okay, so this is, for example, some equation, we'll give it some equation number, and this equation number is, let us say, 0, right? So now in this equation 0, right, in this particular equation, if only first term is present, then the given data hold is called a zero order hold, ZOH, right? Zero order hold. Now let us see what is the first term in this. So the first term is YAT is equal to YAKT, right? So this is the first term. So YAT is equal to YAKT, where T lies between kt, either it is equal to or greater than kt, or it is less than k plus 1 t. So that means t lies between the two successive samples here. So t in this case will be equal to 1. So yat is equal to yak, right? So now this is, this is the output of a zero order hold. So okay, so if you give some sample to a zero order hold, it will give you this kind of output. Now if you see in the previous diagram here, this output belongs to the zero order hold. Okay, so this is the output of zero order hold. For first order hold we have different kind of output. Okay, but the mostly used hold circuit is zero order hold because it gives us more relevant output. Now it is very important, as because we have discussed this many times in our previous lectures, that it is very important to have the signal reconstructed in its actual form. Okay, so to reconstruct the signal in its actual form, we make use of these hold circuits. Now, what hold circuit does, for example, here, this is the actual analog signal, which is input, and this is the output, right? So, in the previous lecture, also we discussed the same thing. So, we have these samples, for example. So, now this is an analog signal converted into sampled, quantized, discrete, and digital. Now, we have to convert this back to the analog form. Now, what we will do is we will hold this sample till the next sample value arrives. So as soon as the next sample value arrives, the output will jump to the or fall to the next value, next sample value. Similarly, this sample value will go as it is till the next sample value arrives, and so on. Okay. So now, so this is the for the zero order hold. Now, if we have two terms, okay. So if the first two terms are present in equation 0, then this analog output is equal to ya kt plus t minus kt divided by t, and we have y kt or ya kt, right, and minus ya k minus 1 t, right. So this is for the first order hold. Now in this, you can see we have two terms. So when we extrapolate the output signal based on the given samples, so we will get some analog output which is given by YAT. Now let us proceed further. Now any sample and hold circuit, so any sample and hold circuit performs two functions, and these are extracting the samples, and the second is holding the result for, fixed for one period, that is for one t, capital T. Now let us see the transfer function of zero order hold, right? So the transfer function of zero order hold can be given by this equation, where H indicates hold, O indicates this zero. So the transfer function is basically the ratio of Laplace of output with the Laplace of input with some initial conditions zero. So it is given by Z inverse, or because we are converting it into continuous, so we will not take Z inverse. We will take Laplace inverse of the impulse function GHOT, right? So why we are taking impulse function? Because if we see, because we have discussed that only one term is present, one sample is present in the uh, output equation, that is YAT. So that means if you see this diagram here, so if you, there are, let us say, four samples. For example, this is at 0, this is 1, this is 2 and 3 and so on. So if we have to indicate this, so we can indicate this like this: x1 delta t minus t, right, or t minus 1, right? Okay, so what is this? This is the scaled delayed impulse function. This is the scaled delay impulse function. Any given, just try to understand, any given sampled sequence. For example, we have these samples here like this. Okay, so there are certain magnet amplitudes of all these values. So this is 0 sample, 1 2 3 4 5 and so on. So this is some xk, for example. So this is x0 and this is your delta k, right? Because this sample is delayed by 0 sample. As we know that impulse sequence or sample sequence exists at 0th, uh, for k is equal to 0, and it is 0 elsewhere, right? So let us find out this one. So we will add this one. Now this sample is x1, so we will take x1, and because this sample is delayed by 1, so we will write delta k minus 1, right? Then we have x2, where x0, x1, x2 are the amplitude of the given samples, and this sample is delayed by 2, right? So we have delta k minus 2 and so on, right? So x0, x1, x2 and so on are the amplitudes of the given samples, right? Or values of the given samples. So that means we can represent any given sample sequence as the scaled delayed impulse sequence, right? Now we can effectively extract, by using the zero order hold, we can effectively extract the samples from the given scaled delayed impulse sequence, right? Now, so we can say that this is a, delayed impulse function for which we are finding out the transfer function, right? It is a zero order hold. So so let us see. So this can also be written as, because this is a Laplace transform, so we will write it like this: 0 to infinity. We will write its Laplace equation GHOT and E minus ST dt. So this is its Laplace equation. Now we also know that this particular exists only for the zero sample, for elsewhere it is 0. So we will write here GHO, it is the impulse function. So it is 1 for t is equal to 0 and 0 elsewhere, right? So we will rewrite this equation. So this is GHOS. So GHOS, the transfer function will be this one, 0 to t. Now, because we have considered this sample, so we will replace this for in, with t, this infinity with t, because now we are finding out the transfer function for a particular time period instead of the infinite uh, function, because infinite function we have considered as 1 here, e minus st into dt, right? So this will be 0 to t e minus st dt, right? So here zero order hold transfer function will be then 1 minus e raised to the power minus st divided by s. So this is the transfer function of a zero order hold circuit, right? Of zero order hold, right? Now, now if we have to represent this whole process of sample and hold, right? So the block diagram representation of the transfer function model of the sample and hold circuit or operation can be shown as, so we have an analog signal XAT. We will sample this. The sampling rate is T, for example. So after sampling, we will get a sampled signal, analog signal, input signal. So we will put it, or we will give this to some zero order hold circuit. So it will give us some analog output YAT. Okay. So the input to this is the input. So input is an impulse function, and impulse function exists for k is equal to t is equal to 0, right? This is one. So this is our unit impulse function, which is delta t, which is 1 for t is equal to 0, 0 elsewhere. Okay. Then on this side we have output. So output is the, now because this sample is 1, and some at first sample, this is at 0 t, for after some time t we will have all the values 0. So let us say that time is capital T. So at 0 we have the magnitude 1. Okay, this is YAT, right? Or not YAT, in fact we can write 0. This is uh, the impulse function as an output, means it is its when we give this input to some zero order hold, how will that zero order hold circuit give us some output? So it will keep on holding the value at same point, and as soon as the time next time comes, so where the value of zero, where the value of this impulse function is 0, so it will definitely fall to that 0 value. So this is uh, the output of the this circuitry, right, which in turn becomes the analog output, right? So we can also represent this as XAT is the input. Then we have the sampled signal where it is sampled with the rate T, and then we have the transfer function of zero order hold, which is 1 minus E minus ST divided by S, and then we have the uh, YAT. Now the Laplace of this XA is XAS, and the Laplace of this is YAS. So that means we can also represent in terms of the Laplace transform. And because here we are getting some sampled uh, signal, so its Laplace is X star S is equal to summation k is equal to 0 to infinity. We have x k into E minus SKT, right? So this is the transfer function of zero order hold. So in this particular lecture, we have gone through uh, the concept of zero order hold. So zero order hold is nothing but the order of the hold circuitry, which is 0. So this can be understood from this particular equation number 0 here, right? So if we have any sequence, which is this one, the output sequence. So this is the output of digital computer, right? Which is converted into analog by using D to A converter, and the output of analog digital to analog converter is YAT, right? So this YAT can be obtained by getting the Taylor series expansion of the same about T is equal to KT. So YAT can be expressed in this form, right? So we have YAKT, then Y dot AKT, and so on. So this YA dot KT term is the second term basically. So it is nothing but the first derivative of ya with respect to time about t is equal to kt. And we can write this dy by dt in terms of the difference equation also. So the difference equation is given by equation number 1. And similarly for the second derivative, that is y dot dot a kt, we can write this equation number 2. So we can put this y a kt minus y a k minus t and replace this from equation 1 and equation 3 to equation 2. So on doing so, we have got equation 4. So if we see in the equation number 0, if this first term is only present as the output, so it is zero order hold. If first two terms are present, it is second order hold, first order hold, sorry. If first three terms are present, it is second order hold, and so on, right? So this was all about today's lecture, and thank you so much.